Alright, time for a boiled potato. Time 0, the boiled potato is taken from a pot in which it was being boiled, I suppose, and left to cool in a kitchen, presumably the same kitchen in which it was cooked. Who knows? The internal temperature of the potato is 91 degrees Celsius at time t equals 0, and the internal temperature of the potato is greater than 27 degrees for all times t greater than 0. This little bit here, if you're like, why are they saying that? What does it mean? Am I supposed to know something about that? It's just so this is legit. If I'm not going to get into the details of why, because it's really not that important, but the problem is if the temperature goes below 27 degrees, this differential equation has some issues, let's say. Anyway, it's just what they're trying to say is it's cooling from this down to that. The internal temperature can be modeled by the function that satisfies this differential equation. And it's not a terrible idea just to try to understand what this differential equation is doing. It's saying that the rate that the temperature is changing at is going to be directly proportional to negative, so decreasing, directly proportional to the difference between the temperature of the potato and the temperature of the room. Right, that's like room temperature. So, for example, at the start, when the temperature is 91 minus 27, that's the biggest that number is ever going to be. So it's 91 minus 27 times the negative 1/4. So it's going to be cooling like steep down. And then as the temperature gets a little bit cooler, this number gets a little smaller, so it kind of tapers like this. So this is like an exponential decay kind of thing. All right. He didn't need to actually go through that to be able to do the problem, but I think it's a good idea to know that. And at time 0, temperature is 91. Write an equation for the line tangent to the graph of h at t equals 0. So t equals 0, I have a point, 0, 91. Use this equation to approximate the internal temperature of the potato at time 3. So I also need to know what the slope is. You can just write m if you want to. I'm going to write it as dh dt. And I get that by plugging in my 91 here. So 91 minus 27. This is not a calculator problem, so we actually have to do math. 91 minus 27 is 64. So negative 1/4 times 64 is negative 16. And that means my tangent line equation, you can write it in terms of x's and y's if you want to. Here, in this situation, this is really y and time is really t. So I think I would prefer to write it like h and t, right, in my point slope form instead of x and y. So h minus 91 is equal to the slope times t minus 0. There's my tangent line, and they want me to use it to approximate the temperature at time 3. So that's going to, plugging in a 3 here, so the temperature at time 3 is approximately, to add the 91 over here, 3 times negative 16, that's negative 48 plus 91. You can just leave it like that if you don't feel like doing the math. As long as it's correct, then it's correct. But that's 43 degrees Celsius. All right. Part B. Use the second derivative to determine whether your answer in Part A is an underestimate or an overestimate of the internal temperature. Okay, so before I even think about that underestimate, overestimate, they're saying use that, so I need to find that. So the second derivative, that's the derivative of the derivative. So if I take the derivative of this, it just gives me the second derivative, right? Derivative of that is that. And then the derivative of this, if you want to distribute this or just kind of like mentally distribute this, plus 27 over 4, just so you can see that this is a constant, so when I take the derivative, that's going to go away. And then that's negative 1/4. That's how you make a 1, like that, fourth. And then when I take the derivative of an h, I get dh dt. And dh dt is that, right? So the second derivative is just negative 1/4 times the first derivative. So that's going to be positive 1/16 times h minus 27. Okay, so what's up with this? Use your answer in part A to determine if it's an overestimate or underestimate. Well, second derivative tells us concavity. And if we know concavity, we can say if we've got a tangent line and it's tangent to a curve that's concave up, then the tangent line will be an underestimate. Because if the curve's concave up, the tangent line will be below it. So, and likewise, if it was concave down, the tangent line will be an overestimate. So it's an underestimate if second derivative is positive. In other words, if it's concave up. And this one, since we know, maybe this is why they told us that the temperature is always above 27. If the temperature is always above 27, then this is always positive. It's 1/16 times this, and if that's always bigger than 27, then that's always positive. So that's concave up, which means that our answer in part A is an underestimate. It's like this. Here's our tangent line, there's our concave up curve. So it is an underestimate. They like that, the College Board. They like doing that second derivative tangent line underestimate, overestimate question. Pretty good chance you're going to see that somewhere on the AP test. For times less than 10, an alternate model for the internal temperature of the potato is this function here, which satisfies this differential equation. Find an expression for g of t. So that means solve this differential equation. Based on this model, what's the internal temperature at time 3? Okay, well, this is the only way we know how to solve differential equations is by doing separation of variables. So I'm going to move, the dg has to stay on this side, and so this, I'm not going to bring the negative sign with this when I move it over. I'm going to move g minus 27 to the negative 2/3 power. I'm going to move that over, and then I'm going to leave the minus sign. It's like a negative 1. You can write the 1 there if you want, dt. I always, if there's any kind of constant or whatever, I always leave that on the right-hand side. I think it just makes things a little bit simpler. Okay, so there's my separation of variables. What's the antiderivative of this? Is just a g to the first power inside here, so there's no u substitution or crazy stuff necessary. It's just power rule. So to take the antiderivative, well, let's first just write in here that we're doing that. So the antiderivative of g to the negative 2/3, so add 1 to the exponent. It's 1/3, and then you divide by the new exponent. Dividing by 1/3 is the same as multiplying by 3. So that's the antiderivative of that. Equals the antiderivative of negative 1 is just minus t plus c. There would be a c on both sides, but we just consolidate them always on the left. Okay, and I know that my initial condition is 0, 91. At time 0, temperature is 91. So I'm going to go ahead and solve for c right now. So plugging in 91 for G. So I already know that 91 minus 27 is 64. Is equal to minus 0 plus C. And 64 to the 1/3. 1/3 power is cube root. The cube root of 64 is 4 times 3 is 12. Sorry, sometimes in calculus class you have to do some math. So there you go. This was a no calculator problem. So they're putting us under some stress here for the math. But we can do it. And then we go back to this here. So I got my 12 now. So 3 times G minus 27 to the 1/3 is equal to minus T plus 12. Okay, now they want us to find an expression for G of T. That means we want to solve, like we're solving for like y equals, but G is the variable of choice here. So I'm going to multiply, or divide both sides by 3, rather. I divided that side by 3, and then I'm going to cube both sides to get rid of that. And I can't do that one term at a time. I have to do the whole thing because math. And then I'm going to add the 27. And that should do it. There's my expression for G of T. And based on this model, what's the internal temperature of the potato at time 3? Well, G of 3 would be, this is plugging 3 into this. So 3 times negative 1/3 is negative 1, plus 4 is 3. 3 cubed is 27, and 27 plus 27 is 54. It's a little bit reassuring that we got something that we knew in part, that here in part A we estimated it here, but we knew that that was an underestimate, and we got something here that's like a little bit bigger. So it seems at least like it's a reasonable answer. And of course you could check the scoring guide. They're easy to look up and see that in fact it is the right answer. There you go. Enjoy the potato. I think it's cool off enough to eat it now.